Okay, hi. We're going to do some of these application problems. 80 through 84 is a set of problems that is using the techniques from this section, which means you can do U substitution now, and section 5.4, which they talk about the net change theorem. So I'm just briefly going to talk about the net change theorem. We're going to do number 80 here, and the problem asks you to find the total, I guess it's basal metabolism of a man according to this formula here, R of t. And basically what integrals do for you is if you have a rate, this is in k cals per hour, k cal per hour. So this is a rate, and when you put a rate into an integral, then after you take the antiderivative and plug in the bounds, you get the net change from A to B. Okay, and the typical example of that is when we have a velocity, because that's a rate that you use probably more often than some of these other rates. So when you have a velocity, v of t dt, and you put that in, when you do the antiderivative of that, you get the position function, and then you plug in the bounds into the position function, and this gives you the net distance traveled. So when you have a velocity, it's, say, meters per hour, and then you'll get the net distance will be the meters that you traveled in that given time period from A to B. So when you put in some other rate, here it's k cals per hour, you're going to get the integral of this. The integral of r of t from A to B is going to be, you can put the dt in there, but anyway, the integral from A to B is going to be the net change, in this case, in kcals. Okay, so that's what the problem is asking you to do, is to just take that, and when they even put it in there, they put it in there for you to, they give you the integral to do. Okay, so what they're saying is, what is the net change, or how many kcals is a young man going to burn, if that's the formula that governs it. So the integral from 0 to 24, because it's a 24-hour period, and the rate is measured in hours. So 1 day is 24 hours because the rate is in hours. Put the integral, put the function in, 85 minus 0.18 cosine pi t over 12 dt. Integrate that, you get 85t. Okay, now the antiderivative of cosine is sine. Okay, but you're going to have this pi t over 12. So let's see if you follow this. I'm going to have minus, I'll have the 0.18, but I'll have a sine of pi t over 12. Okay, now when I do the derivative of this to get back to that, I'll get a cosine, which I want, but I'll also get a pi over 12, which I don't want because I want to get back to this right here, which doesn't have a pi over 12 in it. So I have to put a 12 over pi as a preemptive strike. And that's the way I can do the antiderivative without doing the U substitution. Okay, I hope you're able to follow that. Okay, now I'm ready to plug in the bounds. I'm going to get 85 times 24 minus 12 over pi times 0.18 sine of, it'll be 24 pi over 12, which is 2 pi. And then when I plug in 0, can you see that you get 0 for both terms? Because I'm going to plug in 0 here, get 0. Sine of 0 is 0, so the second term will be, it'll be 0 minus 0. Okay, and then actually this one here is also 0. So the answer is 85 times 24, which is 2040 counts. Number 81. Okay, this one's about an oil storage tank, and it ruptures, and then oil leaks, and they give you the rate. So the rate is R of T equals 100 E to the minus 0.01 T. And this is in liters per minute. And they want to know how much it leaks in the first hour. So first hour equals 60 minutes because the rate is in minutes. So we got to get that part right. So we're doing an integral from 0 to 60. We're going to put R of T in here. And then since this is in liters per minute, what this is going to give us is the total liters, total liter change in 60 minutes. Okay, so let's find it, or the net, it's the net change. Okay, put it in, 0 to 60, we have 100, let's put the 100 out here. We have e to the minus 0.01 t. Okay, e, the antiderivative of that is, well, you got to have e to the minus 0.01 t, so that when you take the derivative, you get back to this. But if I took the derivative of this guy, I would get an extra minus 0.01 on the outside, which I don't want. So I'm going to put a 1 over minus 0.01 to compensate for that. And then I'm going to evaluate that from 0 to 60. Okay, we can do a little housekeeping here with that minus 0.01 on the denominator there. The minus 0.01 on the denominator is, it's like, it's a 100, right? It's 1/100th, so when you flip it, it becomes 100. So really, what you have here is a minus, a little extra. Okay, we have a minus 10,000 because it's 100 times 100. This is really in the denominator as a, this is 1 over 100 in the denominator. So it's really 100 in the numerator. And there's a minus there as well. Okay, and then I have e to the minus 0.01 t evaluated from 0 to 60. So I have minus 10,000 e to the minus 0.6 t, or sorry, 0.6, just 0.6. Here, let's just put it in like this. It's minus 0.01 times 60 minus e to the 0. Okay, so then, so here's what I'm going to do. This is 1, and I'm going to put this minus inside. So I'm going to have 10,000 times 1, because when the minus goes in, it cancels this, and this becomes the positive one, and it becomes first. Then minus e to the minus 0.01 times 60. Okay, and then when all the dust settles, that is 4511.9 approximately, which is 45. 12 liters. Okay. That takes care of 81. Number 82 is about bacteria. It starts with 100, or sorry, it starts with 400. And it grows at this rate. R of t is 450.268. And then we have E to the 1.12567 T. Nice of them to put all those decimals in there for us. Okay, and then we want to know how many bacteria will there be after 3 hours. Okay, what's the rate here? It grows at a rate of that many bacteria per hour. And they want to know about 3 hours, so our integral is going to go from 0 to 3. Now this tells you how fast it grows. This is the growth, but it starts with 400, so it's 400 plus whatever you get during the first 3 hours. So I'm going to put all this stuff in. 450.268 e to the 1.12567 t. 400 plus, now I'm going to integrate. Got that 450.268 coming along with us. Now, when I integrate that, I'm going to have to get 1.12567 t. But if I were to differentiate that, I would get this number right here in front, but I don't want it, so I'm going to put 1 over 1.12567. So that when I differentiate that, I get back to this exactly. I'm going to evaluate that from 0 to 3. Okay, when all the dust settles, we get 400 plus, okay, I'm going to plug in the 3. So basically we have 450.268 over 1.12567. And then I'm going to have e to the 1.12567 times 3. And then I'm going to plug in 0. That'll give me e to the 0, which is 1. So minus e to the 0, which is 1. This is e to the 0. Okay, then you can put that in your calculator. And I already have, so I will give you what I have here. It looks like a 400 plus 11,313. And so we've got 11,713 bacteria. You could say this is approximate. Okay, there you go. Number 83. Number 83 is about breathing cycles. It says a full respiratory cycle takes about 5 seconds, and the maximum rate of airflow is about 0.5 liters per second. So then they give you a function. This explains in part why the function f of t equals 1/2 sine of 2 pi t over 5. So there's the divide by 5 is the 5 seconds. And the 0.5 liters is the maximum. That's when sine is 1. So that would give f of t is 1/2 when sine is 1. That's what they're describing in the first part. Okay, so that models the rate of airflow in liters per second. This is the rate of air flow. Okay, so if we were to put that in an integral and add it up, if we put the bounds of the integral in seconds, then it's going to tell us the total number of liters that flowed in. And it says use the volume of inhaled air at time t. So they want to give you a formula to find the volume of inhaled air at time t. Okay, well they did a little tricky here. So we want to, let's see, find airflow at time t. Well, so that would be this, right? We could have an integral from 0 to t, but the problem is we don't want to have we already have a t here, so they kind of messed with us a little bit. So let's just change it. Let's do f of s ds. Let's just switch it to s instead of t, and then our final thing will have t in it. Okay, so this is the integral from 0 to t of, put our 1/2 out here. We have sine 2 pi s over 5 ds. And then that'll be 1/2. When we integrate that, I'm going to get a minus cosine 2 pi s. Probably a bad letter because of the 5. They look a lot alike. In fact, it is a bad letter, but I'm going to go with it since that's what I did. Okay, and then, okay, so that would be the antiderivative, but if we took the derivative of this, we'd get an extra 2 pi over 5 out, right? When we took the derivative, we'd use the chain rule, but then we don't want that, so I'm going to put a 5 over 2 pi as a preemptive strike waiting for me. And then I'm going to evaluate that from 0 to t. So it looks like I have negative 5 over 4 pi. Okay, and then I'm going to plug in the thing. So I have cosine of 2 pi t over 5 minus cosine of 0, which is 1. And so we can say our final formula. So volume of, or the airflow. So liters, it's in liters. So let me get that. I don't want to use volume here. It's good, but okay. So airflow at time t. Okay, that's going to be. I'm going to put the minus in, and the 1 will come first. So it'll be 1 minus let's go 5 over 4 pi times 1 minus cosine of 2 pi t. That should be the answer here. Liters. Okay. All right, last one, number 84. Here's our big formula. dx dt is 5,000 times 1 minus, and then we have a fraction over here, 100 over t plus 10 squared. That's our big formula for the rate of production of calculators. So this is number of calculators per week. And the question is asking us find the number of calculators produced from the beginning of the third week to the end of the fourth week. So we want beginning third week to, oops, getting a little frisky with that I pencil here. The beginning of the third week to end of fourth. Okay, now there's a little subtlety going on here. Now, if we let's say the function when we integrate this is x of t, so that guy right there is x prime of t. This is Robert. This is Bob. Okay, so we got the same guy, different name, but x of t will be what you get when you integrate. So, and in the wording of the problem, when you look at it, I'm not going to write it out, but it says after t weeks. Okay, so this is the number of it'll be the number of calculators after 2 weeks, which is the beginning of the third week. So what we really want to calculate is, this is what we want. It's x of 4, because remember, x of t will be the function that we get after we anti-differentiate this. And we want to plug in the 4, so that'll give us after 4 weeks, and then we want to subtract off where we started, which was after 2 weeks. So it's not x of 3, because that would give you the end of the third week. We want to do the beginning of the third week, which is the end of the second week, so it's minus x of 2. That's a little issue there in the problem that you have to pick up on. And what is this? This is the integral from 2 to 4 of dx dt. Okay, or if you like, you can put the x prime of t in there. But nevertheless, we have, let's give myself a little space here. So we're going to have 5,000 times the integral from 2 to 4. I got to have that formula there. Then it's 1 minus 100 over t plus 10 squared dt. Or is it x? It's x. The right letter here. Oh no, that's t. Sorry. Okay. Jeez. Outthinking myself here. Okay, ready to go. So let's integrate. Put the 5,000 out there, leave it there. Okay, when I integrate the 1, I get a t. When I integrate this guy here, I'm going to get, it's really t plus 1 to the negative 2. So when I add 1 to that, it's t plus 1 to the negative 1. So I'll have t plus 1 in the denominator. And I still have that 100 up on top. Okay, but then I divide, so it's, let me write it out here. So it's t plus 10 to the negative 2. So when I add 1, I get negative 1. Then I need to divide by that negative 1. So that makes this a plus. And then I'm going to evaluate that from 2 to 4. See if you believe that. In the meantime, I will keep going. I'm going to have 5,000. When I plug in the 4, I get 4 plus 100 over 14 minus, when I plug in the 2, I get 2 plus 100 over 12. When all the dust settles, we have 4,048 calculators. Okay, there you go. We have 81 through 84 in the books. And then the next series will be the 85 through 92. Those are all kind of theoretical questions. Maybe I'll do them all in one video. I don't know. We'll see how it goes, but I'll stop now.